Hey everyone, and welcome. Today, we are going to tackle the big three, the core actions of set theory. We're going to break down, how sets combine, where they overlap, and how they define what's not in them. So let's jump right in.
This quote just hits the nail on the head. If set theory is a language, then these operations, they're the verbs. They're not just some symbols on a page. They're the action words. They tell us exactly what we're supposed to do with these sets.
So what we're really digging into are the big three essential operations. We're going to see how sets can merge together, where they find that common ground, and, this is the cool part, how we can define everything that's actually outside of them.
All right, first up on the docket, union. I like to call this one the great combiner. Just think of this as the most inclusive, welcoming operation of the bunch. It's all about bringing everything and everyone together into one big group.
Okay, so here's the official definition. The symbol, well, it kind of looks like a U for union, which is super handy, right? But the most important thing you need to lock in is that keyword or. If an element is in set A or it's in set B, boom, it gets an invitation to the party. It's in the union. Simple as that.
Yeah, a great way to think about this is the united operation. It literally unites everything from both sets into a single, bigger collection. And here's a key detail. Even if something shows up in both of the original sets, we only list it one time in the final union. It's all about that combination, no duplicates needed.
Okay, so we've gone from the great combiner, which lets everyone in, to something a little more exclusive. Let's talk about intersection. See, this operation isn't about gathering everything. It's about finding exactly what's shared, what's in common.
So this is intersection, and its symbol is basically an upside-down U. Now pay close attention here because this is the big shift. Our keyword has just changed from or to and. And that and imposes a much stricter rule. An element has to be in set A and in set B at the very same time to make the cut.
Honestly, the street intersection analogy is just perfect for this. I mean, think about it. You've got two roads crossing, that little square of pavement where they cross, that's the intersection. It's the only part that belongs to both street A and street B. It's the overlap, the common ground, and absolutely nothing else.
Okay, let's put these two side by side because this is where people get tripped up all the time. Union is generous, it takes everything. It's all about or. Intersection, on the other hand, is picky. It only takes the overlap. It's all about and. So one combines the whole shebang, the other just finds what's common. Got it?
So this naturally leads to a question, right? What happens if there's no overlap, like at all? Well, when the intersection of two sets is totally empty, we've got a special name for that. We call them disjoint sets. It's just the fancy, formal way of saying they have absolutely nothing in common.
All right, so we've covered combining sets with union and finding their overlap with intersection. Now it's time for our third and final core concept. And this one's a little different. It's all about looking at everything that's been left out.
But hang on. Before we do that, there's a quick but super essential idea we need to get. See, to talk about what's not in a set, we first have to define the entire world we're playing in. And that world is called the universal set. Think of it as the container that holds every single possible element we could even consider for a particular problem.
Okay, now that we've defined our universe, we can finally talk about the complement. You'll see it written with a little prime mark or a C up top. The keyword here is beautifully simple, not. The complement of set A is just everything inside that universal set that is not inside A.
This is why I love calling it the rebel operation. It basically rejects everything inside the set and embraces everything else. So if you're looking at a Venn diagram and set A is that one circle, its complement is the entire space, the entire universe outside of that specific circle.
And we can actually combine these ideas to create another really useful operation, set difference. Think of A minus B like this. You start with the entire circle of A, and then you just take a bite out of it, removing anything that it shared with B. What you're left with are only the elements that belong exclusively to A.
Okay, I know that was a lot to take in, but you've now got the full toolkit for set operations. So let's wrap this all up with a super concise summary and a fantastic pro tip that you can start using, like right now.
And here it is, your set theory playbook, all on one slide. It's this simple. Union is or, intersection is and, complement is not. Seriously, if you can just burn this simple table into your brain, you've basically mastered the core logic of all set operations.
And now for that pro hack I promised. Whenever you're trying to solve a problem with a Venn diagram, any problem, always start with the intersection. I'm serious, that shared overlap in the middle, that's the anchor for the entire diagram. Once you figure out what's in the middle, all the other pieces just fall into place so much more easily.
So there you have it. We've got the 3 main verbs of set theory down pat. But what happens when you start mixing them together? Well, you get these incredibly powerful rules, like De Morgan's laws. And yeah, they can look pretty scary and complicated. But what if I told you there's a visual trick to master them in literally seconds? Well, that's exactly what we're going to tackle next time.